So I thought I'd continue reviewing today. And there's no class on Friday, by the way, so this is the last one. Final exam is next Thursday, 8 to 10 a.m., May 8th, in Stanley Coulter 239. I'll be sending you an email with a summary of all the information, including my office hours for next week. Any questions about anything or before I start what I had planned? Let's see, I wanted to mention an important skill in these residue problems. The one I talked about last time, I showed you the integral along the t part is related to the integral we want. We're trying to calculate the integral from 0 to infinity of 1 over x cubed plus 1 dx. And so the integral along that L part, if I use this function f of z to be this one right here, and the integral along the L part is the one we want. I showed you how to relate the integral around the t part to the integral we want last time. And so the last piece of this problem that I didn't do, well, I guess there's two last pieces. I got to compute the residue at the one spot where there's a pole, but you also need to show that the integral along the circular part goes to 0 as r goes to infinity. And so there's two ways to think about that. So we want to show the integral along the circular part of f dz goes to 0 as r goes to infinity. And this is a easy enough function that you can just do it with your bare hands in the basic integral estimate. So let's see, the key here is that, let's see, this is in the denominator, so I need the denominator estimate. I want it to be greater than or equal to something. And of course that's greater than or equal to z squared minus, z cubed minus the modulus of 1. The modulus of z cubed minus the modulus of 1, absolute value of that. That's the denominator estimate stemming from the triangle inequality. And let's see, so that's going to depend on whether or not the modulus of z is bigger than 1 or less than 1. But of course we're letting r go to infinity. So this is going to be equal to the absolute value of r cubed minus 1 on c sub r. And if r is bigger than 1, then this is r cubed minus 1 when r is bigger than 1. So what I get is that this is greater than or equal to r cubed minus 1 when r is bigger than 1. And that's the key. So the basic integral estimate, integral along c sub r, 1 over r z cubed minus 1 plus 1, would be less than or equal to the max of the modulus of 1 over z cubed plus 1 on c sub r times the length of c sub r. And so we would get that this is less than or equal to 1 over r cubed minus 1 times the length of that thing is, it's not a whole circle, it's 2 pi over 3 r. Although you could put 2 pi r there because it's certainly less than the length of the whole circle. So you could use the roughest estimate you want there. And that's true when r is bigger than 1, if you want to be picky. And that goes to 0 as r goes to infinity. So that's the careful way to do that, and an important skill. Sometimes when the polynomial inside the integral is not so simple, you could use the basic polynomial estimate, which is an important fact. Use the basic polynomial estimate Remember, if we have a polynomial of, there exists a radius, an r naught bigger than 0, and constants, 0 less than, I'll call little a less than big A, with, let's say we'd have a times modulus z cubed, that's the degree of the polynomial, is less than or equal to z cubed plus 1, that's the polynomial, and that'd be less than or equal to capital A times z cubed. When mod z is bigger than that given radius, r naught. And let's see, if you're going to have something in the denominator, you would want the denominator estimate. That's this one. And so you could use that, you could get that, you could use that little a and see that the integral, when you do it this way, you would get the integral along the circular part is less than or equal to 1 over ar cubed times 2 pi over 3 times r. And that would be when r is bigger than that r naught. That's another way to do it. And that's the way to do it when the polynomial in the denominator is not so simple that you can do the eyeball it and use the triangle inequality. That's not always the case. Questions about that? Yeah.
So you're saying if it was like x squared plus 3x plus 1.
Right. If it was a quadratic, then you could use the basic polynomial estimate and not think so hard about it.
And I guess what form would that take with this? Because I see how it works when it's just two terms. You're just proving that the leading term is less than the sum of the entire polynomial, right?
Yeah, that was in the denominator. So let's see. If I had a polynomial divided by a polynomial, I would use the right-hand side of that in the basic polynomial estimate for the numerator and the left-hand side for the denominator, and I'd get an estimate that way. And it would just depend on the degrees of the polynomial. We've seen that before when we used it.
You only include the highest order term, basically.
Right, the highest order term is the one that determines the behavior for big Z in modulus. That's the beauty of the basic polynomial estimate. Okay. Let's go to the next. I thought this was a good. This is an old exam question. It looks like it does a lot, but it reviews various concepts, including the Cauchy integral formula and higher order Cauchy integral formula and the residue theorem. So let's see, what about that first one? I've got the circle of radius 1, so that's C1, parametrized in the counterclockwise sense. What's that first integral? Yeah, that's 0 because the thing inside is analytic inside and on that circle. 4 is outside the unit circle. So it looks like it's the Cauchy integral formula with the A equals 4. That's by Cauchy's theorem. And let's see. This one has the second one. You could have done that before we did the residue theorem by factoring the denominator, doing partial fractions, and then you'd get the Cauchy theorem. Then you get the Cauchy integral formula. So that was a problem on the first midterm before we knew the residue theorem. But if you're going to do the residue theorem, this would be, I guess a knee-jerk reaction would be to factor the denominator to calculate those residues. But the zeros of that thing are at plus or minus I over 2. Those are inside the unit disk. And those are simple zeros. So a much easier way to do this would be by the residue theorem. And let's see, so we'd get a residue at I over 2 plus the residue at minus I over 2. And those are not hard to calculate because of the, let's see, what's the first one? This would be, there's f of z over g of z in this thing. And the g of z has a simple 0 at those two spots. So it would simply be e to the I over 2 on top. That's the f of z part. And the g prime would be, what would be 8 times z. And the z would be I over 2.
Would it just be e to the I?
Oh, you're right. It's a 2 times that. It's e to the 2 times that. And the other one would be e to the 2 times minus I over 2. And then we get 8 times minus I over 2.
How do you know if something is like a simple zero? Just like
Well, yeah. Oh, let's see. Those are zeros of order 1. I know if I factored it. But look, I just calculated the derivative. 8 times I over 2 is not 0. The value is 0, but the derivative is not 0. So yeah, those are simple zeros. And then you could do the same thing here. You just had to figure out where the zeros, use the quadratic formula to get the zeros. I think when you get the quadratic formula, you get 1 0 that's inside the unit circle and 1 0 that's outside. And it's kind of not fun to factor that, especially when there's a leading coefficient of 2. Although you could probably, it wouldn't be terribly hard to factor that and get the residue that way. But a much easier way is to use the residue of f over g. The same thing I just did here is f of a over g prime of a when g has a simple 0. That means that g of a is equal to 0. And g prime of a is not equal to 0. That's a 0 of order 1. So that's not a hard one. What about this next one? Yeah. Oh, I'm about to do that in this next problem, because this reminds me of the higher order Cauchy theorem. It has a z minus an a to the 5th in the denominator. And there's an f of z staring me in the face there. So it's kind of screaming to use the, I could use the residue theorem here. I could expand e to the 2z in a power series about z equal half, and then distribute that through and figure out which term would be the residue term and do it that way. So residue theorem would work here just fine. Yeah?
So if the residue is not easy to compute, then you want to do Cauchy integral formula?
True. I guess if it's staring me in the face like this one is, then I would definitely, it would be inspired to use the higher order Cauchy theorem. So remember what the higher order Cauchy theorem was. If I have integral, what is it? The nth derivative of f at a is equal to n factorial over 2 pi I integral around closed curve, in this case, f of z over z minus a to the n plus 1 dz. And so here we have a fifth power, so that means that n plus 1 we want to be equal to 5. The n is actually equal to 4. And so that's going to spit me out 2 pi I over 4 factorial. So the answer in this case is going to be 2 pi I over 4 factorial times the fourth derivative of e to the 2z evaluated at z equals a half. And that would be also with the formula you get when you use the formula that I hate for the residue. The limit formula for the residue. That would give you exactly the same thing there. Does that answer your question? Yeah.
So yeah, if, in this case, since the Taylor series of the numerator is pretty easy, or well, it's well known.
Because the fourth derivative is easy. All right, so you can get the Taylor's formula. But if you're going to use the residue theorem there, I would write e to the 2z is a naught plus a1 z minus a half plus a2 times z minus a half squared plus dot dot dot, and then e to the 2z over z minus a half to the fifth. This would be the principal part, starting with here. And you have to think of, what term is going to give me the residue term? It's going to be the fourth order term here, a4 over z minus 1/2. And so a4 is the residue. And so, of course, I get exactly the same answer. But that's using the residue theorem. Question about that? What about that last one, E? What's that integral? Anybody? 0. We could use the residue theorem. That is a Laurent expansion. And there's no residue term. So the residue theorem would tell you that's 0. But this is also the derivative of something. That's d by dz of z to the minus fifth is 1 over minus 5 plus 1 z to the minus 5 plus 1. And so when you integrate a derivative of something around a closed curve, you get 0 by the fundamental theorem of calculus. I just wanted to review as many things as I could in one problem. But also residue theorem. That is a Laurent expansion. There's no residue term, and so the residue theorem would say it's 0. But you'd have to explain yourself if you did it that way. Questions? Yeah.
How come only the bottom one is 0 because it's like a closed curve?
Right, it's closed curve.
Why should that only apply to the bottom one and not the other ones?
Let's see. So those aren't derivatives of some. Let's see. Those aren't derivatives of something. Yeah, that's the problem with those. This one is sort of obviously a derivative of something. The other ones, so if you think about what would go wrong when you try to calculate antiderivatives for those things, it's the residue term. That would give you a log term in the residue. I mean, when you get an antiderivative, it's exactly the residue term that makes you have a log when you want to find an antiderivative. So, trying to find antiderivatives for those ones that aren't zero, you couldn't find a single-valued antiderivative that would give you what you want. That's why they're not zero.
Okay, and if we try to compute the last problem with the residue theorem, like, so why would we get zero?
Well, the residue term is the coefficient of z to the minus 1 in the Laurent expansion. And that is 1 over z to the 5th is the Laurent expansion for z. So yeah, I guess that's kind of 1 over z to the 5th equals 1 over z to the 5th plus 0 over z to the 4th plus 0 over z plus 0 plus 0 times z, etc. That is a Laurent expansion. And so the residue, of course, would be 0. It's kind of... Questions about that one? Any more? Oh, I thought I should say a few words about power series. The most powerful tool we have about power series is the fact that came from the Cauchy integral theorem formula. We had the Cauchy integral formula. And so if I had an omega and I had an analytic function on omega, the deal was if I look about... I did the Cauchy integral formula on circles about z naught. And it turned out that the biggest circle I could stick in here let's call that R. Then the radius of convergence, let's say I have an f of z analytic on omega. Then the radius of convergence of the power series for f about z naught in omega is greater than or equal to that r in that picture. It's guaranteed to be at least as big as that r. And so in this problem, we would look at sine z over z squared plus 9, centered at z equal 4, and ask what's the biggest disk I can put where that would be analytic. Well, let's see. So z squared plus 9, that would have zeros at plus and minus 3i. And so if I'm looking at the picture, I have a plus and minus 3i and a minus 3i, and I'm interested in the radius of convergence about the point 4. And so the biggest circle is clear there. I can stretch out a circle until it just touches those two spots. So be this distance here. Let's call that R. I'm looking at, was it sine z over z squared plus 9. And so that r is the square, what is it? Square root of 3 squared plus 4 squared. Is this a 3, 4, 5 triangle? And so I know that the radius of convergence is greater than or equal to 5 by this important fact. Why couldn't it be bigger than 5? Yeah.
So if it were bigger than 5, then it would converge to some value in poles.
Right. So if it were bigger than 5, the power series would converge even at 3i. And of course, and so if I followed that blue line out to 3i, it wouldn't blow up. But this one clearly does blow up at 3i. So in fact, well, an important thing to know is that sine of z does not vanish at 3i. If it had a simple 0 there, then that wouldn't blow up at all, and I couldn't use this argument. The singularity would be removable. But sine only vanishes at multiples of pi along the real line, even in the complex case. So it's definitely not 0 at 3i. And so the fact that that quotient blows up there means the power series couldn't possibly converge on a bigger circle than that. Because inside the circle, it converges to that function, sine z over z squared plus 9. And so it better blow up. Okay, so it's important to say and r is less than or equal to 5 because of the singularity, because of the pole. Now we know about singularities. That's a pole of sine z, poles actually, at plus or minus 3i. Questions about that? Yeah. Yeah, so
You just set it to whatever value you want at that point.
no, you have to set it to, well,
Well, to the value that it should be, I guess. At that
yeah,
point.
there is the value. So if it, let's see, what's the classic one that log of 1 is 0. So if I had an example, principal branch of log of z over z minus 1. And let's say I would take the about z naught equals 2. You look at that and say, oh, that's got a singularity at 1. And you'd think about, let's see, log of z is analytic. It has a nasty rip. It has a rip along the negative real axis. So it's not even analytic along the negative to any bigger disk. So you might think that, okay, I'm looking at 2 here. You might think, oh, the biggest disk I can stick in here is the disk of radius 2. That's not quite right, but that looks better. So you might think, is the r equal 2? And the answer is no, because that it looks like, wait a minute. No, that's going to be the right answer. The question is, r equal 1 or 2? And I'm suspecting that z minus 1 is a removable singularity, and it is, because log of z has this log of 1 equals 0. Principal branch of log of 1 is 0, and let's see, what would that be? that would be the natural log of 1 plus I times angle 0 equals 0. And it's a simple 0. And d by dz of log of z is equal to 1 over z. And that's equal to 1 at, so let's see, that would, at z equal 1, that would be 1 over z evaluated at z equal 1. That's equal to 1. That's not equal to 0. So 1 is a simple 0 of the log function. Of the principal branch of the log. So in fact, that has a removable singularity at 1. Log z over z minus 1. So if I give it the proper value there, I'm dealing with an analytic function that's analytic on that whole disk of radius 2. So the correct answer is 2. Question about that?
Since the function given is technically not defined at z equals 1, we give a piecewise defined function.
Well, the Taylor series, if I'm calculating a Taylor series, it's not sensitive to that fact that it's not defined at z equal 1. It needs to be defined at z equal 1 because it has a removable singularity. And so it needs to be, from the point of view of the Taylor series, that thing is analytic, fine, nothing bad at z equal 1, even though we haven't defined it there. So the Taylor series doesn't notice that fact, that we didn't define it there. Question?
So the radius of convergence is 2 at this point because the log is not defined at 0, even though z minus 1.
Well, log's not, no. Yeah, you can't make it go beyond that because, for example, that log function has, it jumps. It jumps, it has a different, if I were to follow it this way and follow it that way, the log function has a jump. And if the Taylor series converged to the function outside that a bigger disk, it wouldn't have a jump going those two sides. So there's no way I can make it analytic on a bigger thing than that. Plus log goes bonkers at 0.
So
Right.
it's a question of like making it.
It's an even uglier singularity than a pole. Yeah. So it can't possibly be can't converge on a bigger disk because then I would get contradictions there. A problem I like is there's a L'Hopital's rule for analytic functions. Let's suppose I have a f and a g that both have zeros of order some order n at z naught. Well, remember the fact about zeros of order n means I can pull out a z minus c naught to the n, and then I'd have something left here. This was a power series argument. I wrote out the first few terms and realized that they're all 0 by Taylor's formula, and then I could pull out the z minus c naught to the n, and what was left was a function that didn't have a 0 and was analytic with a power series with the same radius of convergence. So if f and g both have zeros of order n, then I can do the same thing, top and bottom. And as z naught tends to z naught, as z tends to z naught, of course the powers would cancel, and I would get the quotient of those things which are not 0. So those are not 0 when F and G both have zeros of order n. Multiplicity. So that's a fun exercise that demonstrates you know that fact about power series, that you can, when a function has a 0 of order n, you can pull out a z minus z naught to the n times something that doesn't vanish. Question about that? Oh, I thought I ought to review Rouché's theorem, since it's easy to make it. What? Sorry. There it is. So I got a polynomial here, and Rouché's theorem was about simple closed curve. And let's see, what was Rouché's theorem?
If a function h of z is less than a function f of z over an entire.
Yeah, funny. I like the F and G version better than that. But let's see. So it was that h of z. That was the leash length for the dog, and it has to be strictly less than the modulus of f of z. That's me walking the dog, and that inequality says the leash is less than the distance from me to the pole. Let's see, this is going to be a disk. This is going to be a circle of radius 2. And so this is on the curve gamma. So you only need the inequality on the curve gamma. And H and F are both analytic inside and on this curve. Okay. And then the conclusion, so this is Rouché's theorem. Then the conclusion is that F and F plus H have the same number of zeros, counted with multiplicity. Well, let's see, on the circle of radius 2, obviously the biggest thing is going to be the z to the 4th. And so that's sort of that's the candidate for F. We will try. Let's think about that. So on C2, what would I have? I'd have I'm going to write f of z is z to the 4th. And then on C2, the modulus of f of z would be 2 to the 4th. What's that? Oh yeah, 16. On C2. And so we're going to think of this, this is going to be the f. Which means if we're going to look at a plus h, this is going to be the h. And so the h on C2, z cubed, what the heck was it? Minus z squared plus 2. And so I'd have h of z in modulus would be less than or equal to 2 cubed plus 2 squared plus 2, and that's only 14. I hope. 8 plus, yeah.
Is that minus?
No, I'm using the triangle inequality. So let's see, the modulus of h of z here would be less than or equal to c cubed plus minus z squared plus 2, triangle inequality. Yeah, careful about that. And so I get the Richet inequality that h of z is less than or equal to f of z. It's important. It's got to be strictly less than the other one. So this is strictly less than f of z on C2. So it's critical that this be a strict inequality for this to work. So that means we conclude that the f and f plus h have the same number of zeros. F has 4, so our polynomial has 4 zeros. Counted with multiplicity, that's important. In C2. It's important to say counted with multiplicity. Doesn't have to have a single zero of order 4. It could have all possible combinations that add up to 4. It could have a triple zero and a simple. It could have 2 doubles. Or it could have 4 simple. And that's all the possibilities. Questions? Let's see, what else have I got? Oh, we had various kinds of heat problems that we've studied over the semester. I remember what the easy ones are. We had rings and, let's see, so rings about the origin. Then the solution to a heat problem would be, what was it? A times the natural log of mod z plus b. Then I could set my temperature to be one thing on the inner circle and one thing on the outer circle. And I could set them up to be whatever I wanted. That was one case. If I had a wedge, then I could let's see. So this is if I wanted to have a temperature T1 here and T2 here, I could set up the arg function as a jump in temperature, or the arg function has the temperature of 0 on the blue line and temperature of pi over 2 on the green line. And so it's a great idea to try to mess around with the argument function. And when I start messing around, I realize, oh, I might need to multiply by a constant. And then I mess around more and realize, oh, I don't want it to be 0. That has to be 0 on the blue part because the argument is 0 there. And so if I want to mess around and get a harmonic function that has a different value there, I'd have to add a constant here. So I can solve the heat problem there. Okay. And another heat problem I solved, was another one, is by the same idea. I could have this picture and have a T1 here and a T2 here. Then I could use the same argument again. And when you start thinking about that and maybe having so this problem, there's going to be 4 regions. of different temperatures. So I'll have a T1 here, T2 here, T3 here, and a T4 here. Okay, and let's call this point A1, A2, A3. If I wanted to solve a heat problem like that, you would take, oh I should call these something else. I'll call these Z's. Z1, Z2, Z3. Then I would take A argument Z minus Z1 plus B argument Z minus Z2 plus C times argument Z minus Z3. All those would still be 0 on the T4 part. So I need a constant so I can get the T4. The constant would be T4. And then I get a harmonic function in the upper half plane that has exactly the right jumps in the right spots. And if I've got how many constants? 4 constants and 4 parameters to deal with. And it works out perfectly. So you can solve that problem. Well, this problem asks you to find a harmonic function on the unit disk that has different values in the different quadrants. And this was too hard a problem. I gave it one year after reviewing it pretty extensively. But still, the idea is easy, but writing out the calculations are not exactly fun. They're not hard, but I'll never assign it again. But it's good to think about it as a review question. Yeah.
I want to be careful about the branch cuts here with arc. You have to choose different branches. So that
No, this is the principal argument. And that it has exactly the right jumping behavior.
even on the first one with the log, on the annulus,
It's not the log, it's the principal argument, which is continuous up to the boundary and harmonic in the upper half plane.
let's talk about the first example, the first key problem. We have to, so the branch cut will always go through that region no matter what.
This is the real part of the log function, and so it's nice. There's no bad behavior at all. Yeah, that's harmonic. Being locally the real part of an analytic function means it's harmonic. Okay, so that's the setup for this thing, and the realizing that you can use conformal mapping to solve this problem on the unit disk. So let's see, I've got a function, and I want it to be different temperatures on different parts of this circle. So the plan is I'm going to find a linear fractional transformation that maps the circle. I'm going to blow one of those green slashes out to the point at infinity and map it to the upper half plane. So let's see, this one's going to blow out to infinity. And then this one's going to go to Z1, Z2, Z3. I got to think about my bug. I'm crawling from Z1 to Z2. Be on my left. Yeah, so this would be Z1 prime, Z2 prime, Z3 prime, and the point at infinity is out here. And so I could use a linear fractional transformation and solve the problem. And it's not hard to cook up a linear fractional transformation from the unit disk to the upper half